Hey guys, today we're going to talk about if things are differentiable, or if things can be differentiated, or if they're continuous. Okay, so the alternative form of a derivative, it's useful in finding the derivative at a point. Okay, so if we look at f prime of c equals the limit as x goes to c of f of x minus f of c over x minus c. Okay, provided the limit exists. So we're saying that the derivative of c of that function f when we have c is the same thing as the limit as x goes to c of our pretty much kind of looks like our difference quotient. Okay, or we can look at it as this is all chapter 1 stuff too. We're pretty much saying the limit is the same thing, and it has to, if the limit exists, it also has to be it also has to exist from both sides. So going at it from the positive side and going at it from the negative side. Okay, so the big thing for this is we have to understand that the limit has to exist, and for it to exist, it has to be able to differentiate from the right and the left. Okay. So just like chapter 1 where we had to prove that the limit exists, we had to go at it from both sides. We're going to do the same thing here for our to find our derivatives. Okay. So each sided, so like we're saying, each limit are one-sided limits must be equal for it to be differentiable. Okay, that's the big thing for this guy. Okay, some questions. If a function is continuous at a point, is it differentiable at that point? Okay, not always. Not always. It's not always because you can also have some graphs, and we're going to call them sharp turns. We're going to define these later. Sharp turns, which are like our absolute value graphs, like those V's, right? Or we can have a vertical tangent line. All right, and that happens when we have graphs that have these flipping graphs where it starts coming up and then it flips at 0 like that. So we'll go through some examples of those. First here we're going to be at 1. If a function is not continuous at a point, it is not differentiable. All right, that is the big thing. If it's not continuous, we can't differentiate. So when we look at this function, f of x equals the absolute value of x at x1, we should know that this graph, it looks something like this. Right, our graph looks solid point, line, open point. Right, it's going to look like that. We got those little steps going. Okay, it's not continuous. We can look at that at 1, right? If this is 1, 1, 2, 3, 1, 2. All right. If we look at it like that, we can tell that it's not continuous because at x equals 1, the limit does not exist. Okay? It's not continuous at x equals 1. All right. The limit does not exist. Okay? So we can prove that, or we can show that by looking at it from both sides, by going at one from the positive side and the negative side. So if we're looking at the positive side first, all right, if we're taking it from the positive side, I start with just a decimal that's a little bit bigger than my than 1. So oops. So we're looking at 1 from the positive side. Okay. So for our x, right? We're taking the limit of that. I just use 1.01 to plug in, just a little bit bigger than 1. Okay, so that's also going to be 1.01 right there. All right, that's what we're going to use. That's equal to, let's see, 1 minus 1 over 1.01 minus 1. All right, that's going to give you a 0 over 0.01, which is going to give you 0. All right, so the limit, we got 0 going from that positive side. Now, if we do the negative side, we're going to use a number just smaller than 1. All right, x as it goes to 1 from the negative side of our x minus 1 over x minus 1. All right, and I used 0.99. All right, I used 0.99. Okay, so if we do that, it's going to get a 0 minus 1 over 0.99 minus 1. Okay, that's going to equal negative 1 over negative 0.01. Right? This equals 100. Okay? When you get a number like this, you want to look at a couple more. So what I did here was I started plugging in 0.999. I started plugging in 0.9999 to see what I got. And what you start getting is 1,000. Right? You start getting 10,000. All right, what this means is that it's headed to infinity. Okay, so if it tells us if we got one that's headed to infinity and another one that's headed to 0, okay, what that's telling us is that, let's make our little conclusion box over here. Okay, the limit from 1 positive and 1 negative. This one equals 0, this one equals infinity. So it is not equal and not differentiable. Okay? So because those two limits are not equal, we know that it cannot be differentiated or derived. Okay, moving on down. So now we're going to go over an example of a sharp turn. Okay, so as you see, we got an absolute value equation right there. Our graph is going to look something like this, right? The x minus 2 moves us out over there to 2. Our slope here is going to be 1, and our slope here is going to be negative 1. Okay? So now let's start doing what we got to do. We got to look at it from the positive and from the negative side. So if we're looking at our derived formula, we want to look at our limit as it goes to positive 2. So we're going to take our limit as x goes to 2 from the positive side of, I plugged in 2.01 minus 2 minus 0 over x minus 2. Okay, and what you get out of this one is you're going to get positive 1. Okay, and for this x I put 2.01. All right, when we do it from the other side and we take x 2 to the negative side, we get, I use 1.99 minus 2 minus 0 all over 1.99 minus 2. Okay, and you get a negative 1. Okay, and it's like we showed up on this graph. When we look at it from this side, we're getting that positive slope. We see that m is positive. But when we look at it from this side, we see that it's negative. So when we get two different slopes as we approach this one point, okay, right, it's hard to conclude with the tangent line what the slope is at that one point. because on either side of it, at either side, it's different slopes. Okay, so because their limits don't equal, right? Because our limits don't equal, so it's not differentiable. Okay, not differentiable. All right, so we're just using our limits, test it, see if it works. Okay, now we're going to use the example of a vertical tangent line, So we know that graph's going to look like this from what I drew up above. Kind of come up and do one of those guys. All right, so at x equals 0, the limit's 0. Both those graphs are converging at this point. Okay, so we know that they both converge at 0. The limit of this function by itself is 0. All right, but again, we got to look at it from both sides. So when we're looking at it from the positive side, we're going to plug in our limit of x going to the 0 from the positive side of x to the 1/3 minus 0 over x minus 0. Okay, that's going to give us a 1 over x to the 2/3, which, as you can see, that kind of graph as it approaches 0, it's going to take you to positive infinity. Okay? So the limit is going to be positive infinity. All right, if we look at this, we look at our negative side now. X to the 1/3 minus 0 over x minus 0. Okay, you're going to end up with the same result. All right, you're going to still get the exact same result. All right, but just because you get this positive infinity both times, remember, that means that the limit does not exist. Okay, getting infinity means that this limit does not exist. So now all this is telling us is that there's a tangent line, or the tangent line is vertical, at x equals 0. Okay, so the conclusion is that it's not differentiable. Okay? Moving on to some examples now. Best part of the day. All right, find the derivative from the right and from the left. Is the function differentiable, and at what point? Okay, so we're looking at 1. First thing we want to do, we'll sketch a little bit of this graph out over here. Okay, if you remember, I think we did this one early on, maybe even before we got kicked out of school. But this is just going to be that semicircle. All right, just a little semicircle. That's 2, 1, -1, -2, 1, 2. Okay. So here, back to what we're doing. We're going to be taking the limit from the positive and negative side. Okay, so let's start with the limit as x goes to 2 from the positive side. Let's make it the negative. Start. Okay, so if we do that, we're plugging in our points, our function. Okay, and if we look at points from the negative side, 1.9, 1.99, 1.999. Okay, we're going to have 4 minus 1.9 squared. Okay, x minus 2. And if you kind of just think about this, all right, think about what you're going to get. 1.99. Is this going to, think about if these numbers are going to give you a positive number or a negative number. Okay, if you get a positive under that square root, that's going to give you that number over a 0 conclusion, which, if you guys remember, is infinity. Okay, that's the little shortcut with that. All right, now if we go look at our positive side, okay, we're going to do the same thing. Take our 4 minus x squared minus 0 all over x minus 2. Okay, we're going to get, I'm going to be using numbers like 2.2, 2.1, 2.01, 2.001. Okay, we keep using our equation, our 4 minus 2 times 1 squared all over x minus 2 equals, it gives you a negative under that square root, which is the same thing as I, which means we have no graph. Okay, on 2 to the positive. So again, we can come to the conclusion that our derivative limit does not equal, so it's not differentiable. Okay, our limits are not equal, so it's not differentiable. And that's a negative infinity. Sorry about that. It goes to negative infinity right there. Okay, looking at 2, last example, looking at 2. Okay, we got a function, you got one of these piecewise graphs. Okay, again, that first thing we were doing a couple chapters or a couple sections ago. So we got 2 different graphs, and they're connecting at what looks like x equals 2. Okay, so let's first start at how we're going to derive. Look at how we're going to derive this function. We're going to start with going at it from the left and the right, and we're going to use, so really we're going to use the 2 different functions. So when we're looking at our limit, okay, and understand. So we're going to look at the limit as x goes to 2 from the negative side. We're going to look at the limit as x goes to 2 from the positive side. Okay, remember for this guy over here on the left, we can look at our x squared. Right, we're going to do x squared minus 4 over x minus 2. And the way I got that 4 is because f of 2 equals 4. Okay, we start canceling out. Or we expand and we cancel out. We're going to get x minus 2, x plus 2, all over x minus 2. All right, cancel those suckers out. And when you plug it in, you should get 4. Okay, so we got f prime of 2 from the negative side is going to equal 4. Okay, so now let's look at it from the other side. We got it headed from the positive. So we have x plus 2 minus 4 over x minus 2. Okay, if we simplify up top, you end up with x minus 2 over x minus 2, all right, which equals 1. So your f prime of x at, sorry, 2 from the, your f prime of 2 from the positive side equals 1. Okay? And what this tells you, if you look at the left side, what this is telling you over here is that your slope is 4 at x2, at x equals 2 on x squared, or on y equals x squared. Okay, and what this one's telling you over here is that your slope equals 1 at x equals 2 on y equals x plus 2. Okay, that's what those results are telling you. But what we can conclude from those results, all right, what we can conclude is that our derivative limits aren't equal. They're not equal. Okay, they're not equal where the two graphs connect. All right, therefore, they are not differentiable at x equals 2. Okay? We're starting to combine all these things that we did at the beginning or throughout chapter 1 to make sense in chapter 2. Okay, so make sure you guys understand all those properties of the limits, what the definitions of continuity, and understand this process of how to find the limits from both sides of a certain